Okay, let's get started. So we've talked a lot in here about error analysis, and I've been sitting in the back of the room reading these physics papers about neutrino detection. And what seems to be standard in that community is they'll give you a number plus or minus something, plus or minus something, plus or minus something. And then they'll tell you, like, the first plus or minus is, you know, due to this process, and the second one is, you know, like maybe the first one is random fluctuations in nature. The second plus or minus is electronic noise in the instrument, and the third plus or minus is whatever else. So they're really into error analysis instead of just saying the number plus or minus 0.01. They tell you each little piece that went into that error analysis. And I've never seen that before, but it's kind of keep in mind, it's not a bad way to do things. And then the reader really knows you've done a good error analysis. Okay, enough said. So everything we've done in this class so far has been about radiometry, and that's how you measure energy as a function of wavelength and so on and so on. So you're measuring radiance as a function of wavelength, absorption coefficient as a function of wavelength, and of course depth and time and so on. So that's all radiometry. Radiometry is all about what an instrument measures. There's a whole separate topic called photometry, which is all about what your eye sees. Your eye is not a radiometer that's measuring spectra as a function of wavelength. It's seeing all the wavelengths at once and then running it through some kind of function that says your eye is more sensitive to green than it is to blue or red and so on. So that leads to this subject of photometry, and inside of that you get all these topics like visibility and color. You know, radiometry says nothing about color. Color is a perception that your eye plus your brain comes up with in order to you know, describe what the world looks like. So this lecture, we're just going to give you, or I'm going to give you a quick survey of the whole business of photometry. And what we'll cover is under the topic of visibility, we'll derive some basic laws that govern whether you can or cannot see something. And we'll talk about contrast. We'll mention the Secchi depth. We'll talk about point and beam spread functions, which are super important. We just haven't used them in here. We'll talk about color, which is this physiological concept, and we'll talk about how people define color and try to give it some coordinates or numbers that go with it. And that'll introduce this thing called the CIE chromaticity diagram. And there's a Borel-Dula color index, and we'll talk about those things. So, you know, there's the real world with color, and you know, there's nothing a radiometer is going to do very well that will tell you what a butterfly looks like. And there's something about visibility, you know, you see this thing or you don't. Okay, so as I said, when the human eye is the sensor, you're seeing all the wavelengths at once, but your eye is not equally sensitive to all wavelengths. And so we have to come up with these human eye equivalents of radiometric variables and IOPs and so forth. And those equivalents are called photometric variables. So Every radiometric quantity, like a radiance or an irradiance, has its photometric equivalent. The IOPs have their photometric equivalents, and reflectances and so on. So for example, the photometric equivalent of radiance is called luminance, and that corresponds to what we think of as brightness. Okay, so here's a little camouflage exercise for you. After this class, you go to the Bahamas on the way home, unwind a little bit, go do some snorkeling, and you're out snorkeling one day, and so there's a grass bottom, there's little like sea fans and, you know, seaweed, whatever. Here's a little coral head that's got algae and stuff growing on it. So you're snorkeling along. What animal do you see in that figure? Assuming you haven't cheated and looked ahead at my PowerPoint. Could eat, you know. All right, let's see what's there. Oops.
I have to admit I'm screaming when I do this.
What makes a marine biologist scream? Ever been on capture this?
We'll play again in just a second here. It's worth looking at twice.
This octopus for about an hour. When it crept behind the rock and went into camouflage mode, he
Jam the camera down right in its face, so to speak.
prompting it to go from camouflage to a startle defense.
Blanching white very quickly.
And then eating him.
But I followed the animal and finished the dive, and on top of the surface was only about 5 feet deep, and it screamed bloody murder.
I think it's just astounding how that octopus could make himself look like the background of all the little algae and stuff. They're incredible animals. There was a really good NOVA TV program on maybe a year ago about people studying octopuses and how they can do all these just amazing things and how intelligent they are. And since they're not encumbered by a skeleton, they can squeeze themselves down through like tiny little holes, escape from their aquaria, and so on and so on. So if I were a marine biologist, I would definitely be studying octopuses. Okay, so to carry on about this business of underwater visibility, who cares about it? Well, Alexander the Great did. He was one of the early oceanographers, 300 BC, and Alexander got to wondering what it looked like under the ocean. At least this is how the myth goes. And he probably did something that starts the myth. But anyway, Alexander supposedly built in one description, he was a student of Aristotle. He said he built a glass, what they called it, barrel, a glass barrel, and had himself lowered into the ocean so that he could look at all the fish and whatever's down there. And so here's a Greek postage stamp where Alexander's in his glass barrel and they're lowering into the water. Here's another painting of Al in this glass barrel. Now it turns out Al's wife had a little thing going with the boatman. So they cut the chain, which you see hanging down here, and left Alexander the Great on the bottom of the ocean, and they were going to elope. But anyway, some way he got out and went on to conquer half of Asia. But anyway, he cared about underwater visibility. And every Navy in the world cares about underwater visibility. I'm currently funded by ONR for doing underwater visibility work. So you want to know, for example, before you send in the scuba divers, are they going to be able to see what they're interested in once they get there? So you want to have models that can predict underwater visibility rather than predicting PAR or something like that. So the Navy spend enormous amounts of money on underwater visibility work. And that's how this whole field of optical oceanography pretty much got started back in the 1960s, was visibility questions, not You know, no admiral cared about phytoplankton or anything. Here's an amazing picture. These are dolphins swimming through the water and triggering luminescence or bioluminescence at night, and they just light up. I mean, it's incredible. When I was 7 years old, this movie, The Creature from the Black Lagoon, came out and scared me half to death. But it's definitely a good movie if you want to watch one tonight and see what the creature does. So he was interested in underwater visibility because he was always, you know, after these women who were swimming in the clear water. Okay, here's a guy, Liu Bolin, the Invisible Man. So he's in China, and his thing is to have his friends paint him to look like the background. And then he just stands there, and people go by and they don't even see him. And then he says, boo, you know, and scares them half to death. Well, here's what grocery shopping is like in China. Here's a rack of vegetables, and here's this guy is painted to look like a bunch of vegetables. It's just very effective. You know, if you just look at this, you don't see anything that looks funny. And then all of a sudden you notice, oh, there's a person standing there, and you reach up and grab a box of mushrooms, and it's him. So anyway, whatever you want to do to amuse yourself, you know, here's another possibility. But, you know, it's a visibility problem. Okay, so you're on a submarine, you stick the periscope up, and this is what you see. Now, it doesn't look like an island, so it must be a ship. But real quick, what direction is the ship going? You just can't tell. It's just weird. Well, if the ship is not camouflaged, oh, it's easy to see. Oh, it's going in this direction. So starting in World War I, they developed this razzle-dazzle camouflage, or sometimes it's called dazzle painting, in order to confuse submarines and ships and so forth, or submarines and airplanes that were looking for ships. And you would think painting your ship like that would make it stand out even more. You want to paint your ship blue or something so you couldn't see it against the ocean. But it actually, even though in a sense it makes the ship more obvious, it confuses your brain and you can't figure out things like how fast it's going and what direction it's going. So then the torpedo ends up missing the ship. And it was very effective. Ships painted like this were sunk at a lower rate than the ones that were not painted. And one time I was at the Navy SEAL training facility in Coronado, California, basically San Diego. And I was on a small boat going through the harbor, and we kind of came around the corner of a little pier thing, and there was a PT boat thing about the size of the one you went out on, and it was painted like this. And I remember so distinctly, I came around the corner and I'm just kind of looking over there, and then all of a sudden it dawns on me, oh, there's a boat docked there. And my brain simply did not register that as being a boat. It took like 5 seconds or 10 seconds or something. And then my brain some way sorted it out and said, oh, that's actually a boat. Now, if that had been in the real world, I would have already been dead because they would have blown me out of the water before I even saw them. So a very weird thing that you would paint boats like that, but it works very well. Okay, when you're talking to these visibility people, there's 3 terms they use. Detection means that you can see there's something in the water or in the air, but you just can't quite tell what it is. So I see something there, but is it like a scuba diver? Is it a shark? Is it a submarine a longer ways away? I'm not really sure. Then detection says, oh, I can see in general what it is, but not the real details. So I can now see that this thing here, it's actually a fish, or maybe it's a dolphin, but it's not a scuba diver, it's not a submarine. And then there's the identification level, which says, oh, I can now see exactly what's there. It's a great white shark. So I've gone from something in the water detected, classified as a fish, and then identified as a great white. So those terms we'll see in all the papers on this stuff. Absorption and scattering affect visibility in different ways. So here's your perfect image here. And then what absorption does, light leaves this object over there, it's on its way to you. And if the light gets absorbed, you just don't see the object. So as absorption increases, whatever you're looking at just kind of fades away because the light just simply doesn't make it to you. So you no longer see it somewhere if there's enough absorption or if you're far enough away. So the image itself stays nice and crisp, it just fades from view. Now scattering by particles, with our little volume scattering function, what it does is the image will stay steady and it may stay fairly bright, but you'll lose the background detail because the scattering just blurs out the detail of whatever's in the image. And then if you get far enough away, there's enough scattering that you just don't see it anymore because all the light is scattered out. And normally when you look across the Harpswell Sound here, and it's kind of hazy on the other side, that's particle scattering by aerosols in the atmosphere. Absorption in the atmosphere is usually negligible compared to scattering. Now, if there's scattering by turbulence, so you're at an interface where there's a big temperature gradient or a big salinity gradient, or on land, you would be looking off towards the horizon over the road, and there's some mirage, air has a lot of turbulence in it. That again causes small angle scattering. But what happens there is the image tends to break up and it may stay bright, but it kind of twinkles. So when you look at stars at night, they're kind of twinkling. That's because of atmospheric turbulence. So those three effects, absorption, scattering by particles, and scattering by turbulence, do different things to images. Just tuck that away and now you know. Okay, so when we want to talk about can I see something or not, we get into what's called the Radiance Difference Law. So here's something in the water, and that always gets called the target in this world, but there's an object in the water, and there's going to be radiance coming from that, and here's either my camera or my eye back over here. So along the way, some of that radiance will be absorbed, some of it will be scattered out of the beam, there may be ambient light scattered into the beam, and finally some amount of radiance will get over here and be detected. Then from the same distance away, right next to the source, there will be a background radiance, whatever the ocean or whatever it looks like. And along the way, that'll get absorbed, scattered out, scattered in, and get over here and be detected. So we're going to assume that these two paths are basically right next to each other. I'm looking at the object and I'm looking right next to it. So the two paths are the same. The target here is illuminated by the ambient sunlight, and that the radiance reflected off of this target doesn't change the surrounding ambient light field significantly. And then these two directions, the C from the target and the C from the background, those are basically parallel directions right next to each other. So we'll just call it direction C. So the idea here is because this path and this path are basically the same, the absorbing and scattering processes along the way, and if there were any internal sources along the way, those are the same. All that's different is the beginning radiance from the target and the background. So if we write down the radiation transfer equation, which you've all memorized now, you've got dl dr, and r is the direction we're going here. The change of radiance with distance is minus beam c times L. And then there's the integral over all of the ambient directions, scattering light by the volume scattering function into the one direction that I'm looking at. And there might be a source term out here too. Well, let's just call this big integral here, this L star. And now, as I said, the idea is that along these two paths, all the absorbing and scattering along the way are the same. All that's different is how the initial value. So if I write the target radiance change with distance, well, that's minus beam c times the target radiance plus the path length term here. And then for the background, the change in the background with distance is minus beam C times the background, plus exactly the same thing here, because this term is going to be the same for the two paths. Okay, so now all I have to do is subtract this from this, and these two terms will subtract out, and I'll just have the difference in those two. So we do that subtraction. There we have that. This is a nice little differential equation for the difference here. The rate of change of the difference in the target and the background with distance is minus beam C times the difference. So you dig out your differential equations book and you realize, oh yeah, that's simple. The solution for the difference in the target and the background at some different distance R is the difference when you're up close and e to the minus the integral of beam C over the distance R. And you usually assume the water is homogeneous, so beam C is homogeneous, and this just becomes e to the minus CR. So the big deal here is that even though each of these radiances, as it goes along, is being changed by the absorbing and scattering properties of the water, but the difference in the two radiances is being changed only by the beam attenuation coefficient. And you don't have to mess at all with knowing what the volume scattering function was, just the beam attenuation coefficient. So this is called the Radiance Difference Law. Okay, now we get in, we'll see that again in a minute. Okay, so now we get into what are called luminosity functions. And there's a thing called the photopic luminosity function that gives the relative sensitivity of a normal human eye to different wavelengths. And there's one for daylight, there's one for nighttime. So the one in the daylight is shown in green here. That's called the photopic luminosity function. And that's what your eye uses in bright light. And that's the sensitivity of the cone cells in your eyes that see color. And then at nighttime, this thing is shifted off to the blue a bit, and it's called the scotopic, or the dim light luminosity function. And that's what your rod cells that see the low light levels at night, but you only get to see in black and white. So these two things are where you start getting into the fact that, that the eye is not equally sensitive to all wavelengths. So your eye doesn't see 350 nanometers at all. It doesn't see 750. It's most sensitive at around 555 in the daytime. It's most sensitive around 510 or so at night. Okay, so we want to make a transition now from radiometry to photometry. And so radiometry is always in energy units like joules per second or watts. The photometric or vision variables are in a unit called the lumen, which is a measure of how bright something is. That, subjectively bright as your eye would see it. So the way this works is you take your radiometric variable. So let's say this is radiance, that's watts per square meter per steradian per nanometer. You take this photopic luminosity function, which is non-dimensional, and you integrate over all wavelengths, and you come up with a thing called the luminance. Now there's a conversion factor here that's called the maximum luminous efficacy, is Km, and that's actually 683 lumens per watt. So that's the best you'll ever do at converting a radiometric variable into a photometric variable. It's sort of like the idea of some mechanical process and you're not losing anything to friction, for example. Okay, so anyway, you take your radiometric variable, multiply it here, integrate, multiply by this magic conversion factor, which is actually based on historical studies, and then they finally agreed on this quantity as being the conversion between radiometric and photometric quantities. And that's actually now a fundamental physical quantity, just like the speed of light is. It's just fixed now for all time. So anyway, you get 683 lumens per watt, and you've integrated out the wavelength. So you're left with lumens per square meter per steradian. And there's another unit you'll run into in the SI system called the candela, and that's a lumen per steradian. Just keep in mind that 1 candela is about what you're looking at from a meter away when you look at a candle. And the name came from what they used to call a standard candle. So in 1880, they very specifically defined how you make a standard candle by burning a certain kind of whale oil with a certain kind of wick. And the wick has to be, you know, this long and blah, 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 because there were no, you know, LEDs or anything to play with. So they defined a standard candle, which then got that luminance of a standard candle that was called a candela. So you'll just, you know, have to get used to these terms. So a radiance is getting converted into a luminance with units of lumens per square meter per steradian, or a candela per square meter. Okay, and you can do the same thing. You can take ED and put it in here, and you'll get the radiometric quantity of ED. We'll see that in a minute. Okay, so here's another plot of these brightness functions. So the green is the photopic luminosity function. The blue is the scotopic at night. And here's the performance of a low light video camera that I've been working with, all normalized to 1. And then here now is this photopic curve with the calibration put in. So here's your 683 is the maximum value. The scotopic function, the equivalent of that maximum luminous efficacy, is about 1700 lumens per watt rather than the 683. So that's telling you that at night, your eye is more sensitive. It makes better use of what light is there at the expense of losing some visual acuity. You don't see as much detail, and you only get to see in black and white. Now, of course, this is what the camera people show on their website. Fat chance of actually getting them to give you this in a calibrated way so you could really compare it with a human eye. And I'm guessing they may have never figured that out themselves because no customer ever asks for it. But anyway, you can see this video camera, which is black and white. It's seeing a very broad spectrum from basically 400 out to, actually goes out almost to 1,000 here. So you're getting a very, very sensitive camera, but only this black and white image. And I think its curve would be way up here somewhere. I just don't have the numbers to show you. Okay, so here's a question. If you're looking at, let's say, a 350 nanometer laser, what do you see? So shine this ultraviolet laser in your eye. What's it look like? Don't actually do that. Thought experiment. What would you see? Nothing, because your eye is not sensitive to 350 nanometers. So you'll sit there and just cook your eye until you're blind, and you'll never see it. You'll never have any perception of brightness. Whereas if you go out and, you know, look at a 532 nanometer laser, like that's what this is, wow, that would be incredibly bright, and you would blink immediately. Okay, so just a little table here of some typical luminances. So I took the black body radiation spectrum for the temperature of the sun and plugged that in, did my little integration, and that comes out at about 2 billion lumens per square meter per steradian, or 2 billion candela per square meter. That's above the atmosphere. The solar disk at the Earth's surface, sun at the zenith, you can just think of that's about 1 billion candela per square meter. So if you look right at the sun, which once again, don't do that, boys and girls, but if you did it, you know, that brightness of the sun is about 1 billion lumens per square meter per steradian. And then you go on down the road, you know, if you're looking at the bulb of a 60 watt frosted light bulb, you know, it's really bright. You can barely look at it. That's about 10 to the 5th candela per square meter. If you look at the moon, and you can't do that, that's more like 6,000. You know, a nice bright full moon on a clear night. And you go on down to where if it's an overcast sky and a moonless night and you're in the middle of the forest, you know, you're looking at like 10 to the -5th for these numbers. Okay. The only one of these I remember is looking right at the sun. It's about 1 million. And, you know, all the others, I have to go look them up if I need the number. Okay, so now here's off the package of your light bulb. And it says, this light bulb here is giving you 820 lumens, costs you $7 a year to run. It's a 60-watt bulb. Well, then you say, wait a minute, 60 watts, and it's 683 lumens per watt. I should be getting about 41,000 lumens out of this bulb. So what's going on there? Well, the bulb is at a temperature of 2,700 degrees Kelvin. Plug that into the black body radiation spectrum, and you get the red curve. So that's what the light bulb is putting out. But here in the green is your photopic luminosity function. That's what your eye is seeing, is just this little bit of the curve right here, which is about 2% of the total energy. So bottom line is your average incandescent light bulb, you're paying for 41,000 lumens, and it's really only giving you 820. That's about 2% efficiency. Colin.
So I would say that that is true for the light, but in terms of the energy, if you're using these bulbs in your chicken barns to light your chicken barn, it's also warming them up in the wintertime.
Yeah.
When you use LED lights, there's no warmth coming off of that. And so, you know, when people are moving away from these type of light bulbs, it's really sad for the chicken farm.
Yeah. Yeah. So the bottom line is
something to think about.
Incandescent light bulbs are great ways to heat chicken coops in Maine in the winter. They're terrible ways to light your room. That's why all this move to LED and so forth is to get more of the energy to put out at wavelengths down here where your eye actually sees it. So you'll notice they don't say on the ad here, 98% of your money is going to heat, not to lighting the room. Can't imagine why they don't say that. Okay, anyway, for when you have an irradiance like ED, you run it through the equation and you get an illuminance rather than a luminance. So radiance to luminance, irradiance to illuminance. So you can do the same thing. You can go back to this equation, you plug in ED, and out will come the illuminance out here. And also I should comment, the convention is you have a radiometric variable and you stick a little V on its subscript to indicate the photometric variable, and the V stands for visible. Okay, so we come back here, you can do that with an ED, or you can take the luminance and just stick it into the same equation. So luminance times the cosine theta integrated over solid angle, that gives you the corresponding illuminance. So it's just like radiance integrated here gives you irradiance, luminance integrated like this gives you illuminance. And you can do the same thing. You can define a photometric reflectance of, you know, KDs for photometric variables. They all carry through exactly like the radiometric variables, but they're now a broadband measure. And so here's some typical illuminances, equivalent of say ED. So the one I always remember is a well-lit room is, you know, a few hundred. In here right now, it's probably more like 300. If we turned on all the lights, maybe it's 500, something like that. And then goes down to, you know, very small values. There's like 9 orders of magnitude between outside on a bright sunny day and a moonless night in a heavy forest, etc. There's just the numbers there. And the units of illuminance now are lumens per square meter. Remember when we had luminance, it was lumens per square meter per steradian. Now we've integrated over direction. So illuminance is lumens per square meter, which is always called lux. That's just an old term in the literature. So if you go to the photography store and you ask them for a light meter because you want to measure the light in this room in lumens per square meter, they'll have no idea what you're talking about. But tell them you need a lux meter, and oh yeah, we have plenty of those. So that's just a term there that people will always use. This room is 300 to 500 lux. Okay, enough said there. So for an IOP, like beam C, for example, what you do is you take your IOP, you weight it by the photopic luminosity function and by the radiance distribution of wherever you're measuring this. And then it's normalized by an integral of radiance over y bar. So this still has units of per meter, but it's now been integrated over all wavelengths, or effectively you can integrate from like 400 to 700 because outside that range is 0. And this is called the photopic beam attenuation. So notice it depends on the viewing direction. If I'm in homogeneous water, it's not in the middle of a crystal or something, beam C measured this way is the same as it is measured this way. For the photopic equivalent, because it's got this radiance weighting, in theory, it will depend on whether I'm looking this way or this way. But in practice, it really doesn't make much difference. So you can do a lot of measurements and a lot of simulations, and you'll conclude that the photopic beam attenuation is usually within a few percent of the beam attenuation at 555. You know, that's where your eye is most sensitive, and that's the way it comes out. So there's a lot of models where instead of really dealing with the photopic beam attenuation, they just use the regular beam attenuation at 555, and you're good to within a few percent. But in principle, at least, this C here, the photopic C, is an AOP, it's not an IOP, because it does depend on the radiance distribution. Okay, you can go through this little derivation that we did for the Radiance Difference Law, and you come up with exactly the same thing, and it's the Luminance Difference Law, except now it's not a difference in radiances, it's a difference in luminances that your eye would see, and it's the photopic beam C out here, but the equation looks exactly the same. So when I want to decide with my eye, can I see this object over there? I use this equation with whatever the luminance from the object is, whatever the luminance from the background is, and use the photopic beam C, but I'll probably really plug in the regular beam C at 555, and I'll get a pretty good prediction. And then I'll decide that my eye can or can't see this object. Okay, so to make that decision, there's something called inherent and apparent contrast. So the inherent contrast says, if I'm right up next to this thing, or if I'm looking through a vacuum, what's the difference in the target radiance and the background radiance normalized by the background? And that's called the apparent contrast. So I'm right next to it, measure this, what's the difference? Divide by the background. I go further away, then the difference in the target and the background normalized by the background at this distance away is called the apparent contrast. And so you'll notice if the target is darker than the background, so this would be less than this, then the contrast is negative. If the target is brighter than the background, so this is bigger than this, then the contrast is positive. And what if you're looking at a target in a black background? Well, then the game's over because the black background has 0 radiance and you have to do a different analysis. But this is what's normally used to make a decision on whether something's visible in normal daylight or nighttime conditions where the background is not absolutely dark. Okay, so remember those things. then you could take this luminance difference law and rewrite that using this contrast business, and you'll get that the contrast at some distance r looks like the inherent contrast, and then this ratio of background up close to far away, and then the little exponential. And if you're looking horizontally in the ocean, then the background value up close and the background far away are the same if the ocean's homogeneous. So you'll often see people say, well, I'm looking horizontally, this term here is just 1, and that the contrast at distance r is the inherent contrast times e to the minus cv times r. And either this equation or this equation is called the law of contrast reduction. So it's telling you that the contrast is decreasing with distance r, just as this little exponential times photopic c times the distance. So nice, simple little relation there. Now, if you're looking, maybe you're underwater and you're looking upward, then the background is at the object is a different radius than the background where you are, and you just have to plug that in there. Okay, so you'll see that thing used a lot. Here's some examples. Here's a simulation of my background, and I put in a gray target. So think of a Secchi disk, for example. And for this particular thing here, it's not black, it's gray. Right up close at an optical distance of 0, the contrast was minus 0.47, minus because the target was darker than the background. Then I move 2 optical distances away. I can still see it. The contrast has gone from minus 0.47 to minus 0.2. At 5 optical distances, I can still see it. The contrast is minus 0.06. At 10 optical distances, I just can't see it anymore. The contrast is down to 0.02. So there's a little rule of thumb that you lose the ability to see something when the contrast, the apparent contrast, is down to a couple of %. And in the literature, you'll find people use anything from about 1.5% to 5% as their dividing line for when they can see something and when they can't. At airports, the people sitting in the control towers use 5% because they want to make sure, they want to have this margin of safety that when they say, I can see the airplane down at the end of the runway, that they're going to be looking at this case here and not here. So they want to make sure, yeah, I can look down the foggy runway and see an airplane there, and their cutoff is 5%, not 2%. Okay, then if you take, let's say 2% here and say, well, I'm going to plug in 0.02 here, and I'm going to plug in my beam C at 550 and solve for what distance gives me a 2% apparent contrast. Well, you just plug in there. It's about 4 over beam C at 550. So you can go out and look at the bottom of the water off of the pier here and see at what depth can you no longer see a rock or something on the bottom next to the mud on the background. And when that disappears, you can say, well, take 4 times that depth, and that's about what beam C at 550 does. Just a little rule of thumb. Okay, and then as I said, when you go through this whole business, you can't have an absolutely black background. So if you wanted to come up with a rule for, can I see a lighthouse at night when the black background is entirely dark, then you do a different analysis and you come up with something called Allard's law. And this relation here is called Koschmider's law. And that works in the daytime, and this works at night. Okay, new topic, Secchi did. This fellow Secchi only had 1 paper in oceanography, but it was a good one. So he was actually a solar astronomer and a spectroscopist. And he spent his career measuring stellar spectra and the spectrum of the sun, and it dawned on him, oh, look, the sun is just a star. So he was the first person to realize that the sun wasn't this super special thing that there's one of in the universe. It's just an ordinary star. It just happens to be up close. But anyway, he was out on the Pope's yacht one day and got to playing in the water here and lowering this disc in the water and seeing how deep it would go before it disappeared, and wrote this paper on how to determine something about the clarity of the water by lowering a white disc into the water, which is now called a Secchi disc. And that was his only paper in oceanography. So anyway, oceanographers tend to use a 30-centimeter diameter disc and usually has a reflectance of like 80%, something like that. The limnology community studying lakes almost invariably uses a 20-centimeter disc with half black and half white in this pattern here. And search the literature all you want, you will find no scientific argument or data that shows one is better than the other. It's just that the oceanographers never talk to the lake people and vice versa. So we go to different conferences, we go to different bars, you know, and it just never sort of meet. But that's the way it's done. So there's now a couple of models for how to predict the Secchi depth given the water properties and so forth. One of them is called this classic Secchi disk theory, reviewed by Preisendorfer in the Knowledge in Oceanography article. And the basic gist of it is this. You're up here in the air, you're looking down through the water, you're seeing the Secchi disk down here. Now the light that's illuminating that disk is coming from all parts of the surface up there, all sky radiance. So that radiance gets down here, it illuminates the disk, and that's basically ED, and it is decaying with depth like KD. Then that irradiance onto the disk reflects off in all directions because you hope this thing is a Lambertian reflector, but there's one little path of that that makes it up to your eye, and then these paths over here go off somewhere else, so they're not being seen by you. So this radiance is decaying as beam C, and the downward irradiance is decaying as KD. So Preisendorfer works through the math, and then you may lose some contrast if there's waves on the surface, so you have to put in some little factor to take care of that. And you're looking at it with your eye, so you're going to actually use not ED, but you're going to use the illuminance on the way down and the luminance on the way up. Okay, we're not going to go through this, but I just put this in the PowerPoint so you guys can go look at it when you get home. But Preisendorfer starts out and says, well, we're looking straight down, you know, works through the math here, makes the little assumptions about the disk being a Lambertian reflector and so on and so on, rewrites things using the Luminance Difference Law. Here's the inherent contrast, and works through the math, puts in a fudge factor to account for surface loss of what you're seeing, and finally comes up with an equation that says the Secchi depth looks like the average of the photopic KD over the surface down to where the disk is, plus the average of the photopic beam C averaged over the water column from the surface down to the disk. And then there's a little scaling factor here, the gamma, which is typically about 8. And so that's one of the ways that hydrolite computes Secchi depth. Now notice, you can't compute these averages over depth until you know what the depth is itself. So hydrolite actually goes through a little iteration scheme where it starts out and says, well, you know, if I'm a meter down, the average KD and the average photopic there are this much, plug them in now, not quite there, you know, go down a little deeper, and then finally, when this thing disappears using that 2% contrast law, then hydrolite says that's the Secchi depth. So when you look at the bottom of the hydrolite printout, there's 2 or 3 printouts of the Secchi depth. And one of them, there's this one. And then Zhongping Li went back and said, let's look at this whole thing over again. And the Preisendorfer derivation is based on the values of the luminances and so forth at the depth of the disk and so on. Zhongping Li says, maybe it's not the luminances that matter, it's the reflectance. So what's the difference in the reflectance by the disk and the reflectance by the water next to it? And then he didn't make these assumptions about the background luminances being, what do I want to say? The disk doesn't disturb the ambient background. And he decides that, well, the visibility is determined at the wavelength where the disk is most visible in whatever water it's in. And the end result is he finally comes up with a formula that says the Secchi depth is a scaling factor over 2.5 times KD at the wavelength where KD is the minimum, minimum. So in other words, whatever wavelength in this water is the clearest, measured by KD, I'll use that wavelength and I'll plug into this little formula and I'll get the Secchi depth. Now, the nice thing about this is that KD at 490 nanometers is a standard output of all the NASA remote sensing. So in your water, maybe it's really green water and it's clearest over 550 nanometers. Well, then you could use the NASA KD at 490, go back, get one of those little models for KD as a function of wavelength, if you know it in one, and you could get the KD at 555, and then predict the Secchi depth. So this formula allows you to come up with Secchi depth from satellite remote sensing patterns. Very powerful thing. That's why he did that. And he's got a number of papers on this. So here's a comparison between the measured Secchi disk by some guy hanging over the side of the boat and looking, and the estimated value from Zhongping's equation for open ocean water, coastal inland US, Chinese waters, and so forth. And you can see it does a pretty good job. And this is all data pulled out of the NASA CBAS thing. So you may not care at all about Secchi depth when you go to sea, but it's easy to measure it, stick it in the databases along with whatever it was you were interested in. And then people like Zhongping can come out and come up with data sets that have RRSs and Secchi depth and IOPs and all of these things, and use that data in ways that you might not have even thought of. So anyway, what hasn't been done yet is a real comparison between Zhongping Li's equation and the classical Preisendorfer equation. Be a great master's project for somebody. You need to measure the ED as a function of depth and wavelength, beam C, Secchi disk, the disk properties, and do that in a wide range of waters. And my guess is that some waters, one formula will work better than the others. Now, when you run Hydrolite and you look at the different outputs, if you're in very clear water, they're almost identical. If you're in really scuzzy case 2 waters, they may differ by a factor of 2. Yeah, Emmanuel.
I mean, if you go back to the formula, you can see the previous one. You can see where they're likely to be the most different. What do you think? Is it in water that are different? I mean, what property in the water is likely to drive one more than the other? All this attenuation. I mean, both have diffuse attenuation, one has attenuation. And what, so what's the difference between attenuation and diffuse attenuation? What is diffuse attenuation versus absorption? So the biggest difference is likely to be in water where scattering dominates attenuation. If I were to, that's the way I would go to water for turbidity zone and then test these two approaches. That's, I would assume, where they're most likely to be.
And if we gave this lecture first in this class, then somebody could have said, yeah, I'll do that for my project. Anyway, okay, carrying on. Then there's some other models here, one by Zahnefeld and Company. They cooked up basically an instrument where instead of looking at the disk disappearing as you go down, they make a little periscope thing that they can stick in the water and look horizontal. And then you move the disk away horizontally and see when it disappears rather than seeing when it disappears going down vertically. And what they found is that you can predict when the disk will disappear by the little formula of taking beam C at 532, 9/10 of that, add in a little bit, and divide that into 4.8, and you'll get the visual range or the distance when it disappears. That's good to about 10% in a wide range of waters. So it works pretty well. One of these classes, Zahnefeld was here, and he brought his little gizmo, and we went out on the dock and just walk down the dock and see when the disk disappears. And, this works quite well. So you'll see things like this in the literature as well as ways to determine how far away you can see something. Okay, now we get into beam spread functions. So this was photographed in the little fish tank that you guys used the first day. Laser shining into the tank, and down near this end of the tank, you get a very sharp laser beam, and the rest of the tank is kind of dark. And there was some Malox or something mixed into the tank. So as the light propagates through the tank, the brightness of the beam becomes less and less, and the surrounding water sort of lights up and glows. So you go from having a profile like this to this to this. And so the beam is spreading out from multiple scattering here. And so that's described by this thing called the beam scattering function. Remember, the volume scattering function describes how a single scattering event works, and the beam spread function describes how all the effects of multiple scattering add up as you go further and further through the water. Okay, here's how it's defined. So here's your light source, collimated, shooting the light out in this direction, and then you take a plane irradiance meter, the same one you use for ED, and you just shine your light here, and you move this instrument, what's happening here? Move your instrument like this at a radius far away and measure the plane irradiance, measure the plane irradiance here as a function of the off-angle axis theta. And of course, when the instrument is right in front of you, you're looking at the brightest spot. As you go out to the side, it gets darker and darker. So you take that plane irradiance, just think of that as ED, except it's pointed back this way, and normalize that by the power of the instrument. So the beam spread function is defined as the detected irradiance normalized by the power. So this guy is watts per square meter per nanometer. This is watts per nanometer. This thing has units of per meter squared. Okay, so funny story here. Well, I'll hang off on that. We'll define another thing. That's the beam spread function. Then there's a thing called the point spread function. Now the beam spread function, you have a cosine collector here and a collimated source. Then there's another thing called the point spread function, which says I have a cosine emitting source and a collimated detector. So now if I take the intensity of this source, and it depends on this angle gamma, according to a cosine, and it's putting out light in this direction and nothing back in this direction. So I can define the intensity of this source. Remember, intensity is watts per steradian per nanometer. And if I take this little function and integrate over all angles here, then that just gives me the total power being emitted. And then I'm going to define the point spread function as the detected radiance normalized by the power over pi. And notice that also has units of per meter squared. So one time it's a point source, a collimated detector. The beam spread function is a collimated source and a cosine collector. Then, if you want to kind of visualize what's the point spread function, well, look at a bright street light here, and it's really bright here, and it's not so bright here. So just plot that radiance here as a function of angle looking away. That's simply the point spread function. Nothing too complicated. Okay, then here's a plot now of in two different water bodies, or sorry, 2 different days. The beam spread function in water that had 1/c is 6.8 meters, and the next day it had 1/c was 7 meters, so they're a little bit different, but basically they look exactly the same. And at conferences way back when I was, your age, fistfights would break out with people arguing about whether or not the beam spread function and the point spread function were numerically equal. And so finally, after 20 years of arguing, Howard Gordon sat down, went through all the radiatory transfer theory, and proved that these things are actually exactly the same. They're just measured in different ways. So anyway, people usually just work with the point spread function and talk about that, even though they may be looking at how a laser beam propagates, but it's the same thing. Okay, so this point spread function, it depends on the IOPs and it depends on the distance. So here I just had 3 different phase functions, Petzold, one appropriate to phytoplankton, low index of refraction, one, the blue one for mineral particles, high index of refraction. I have Monte Carlo codes that compute beam and point spread functions just by doing lots of ray tracing, seeing what makes it through. And so here's some examples. So when I'm distance of 1 optical depth away, then here's the red curve is the one for the phytoplankton. The blue curve is the VSF, or used the VSF for the mineral particles. And you can see they're considerably different. And then here's 10 optical depths and 30 optical depths. Now, notice for the low optical distance here, this has kind of the same shape as the volume scattering function. The units are different, but the shape is kind of the same. Now that makes sense because at low optical distances, I probably only have about 1 scattering event. So the beam spread function is only recording 1 scattering, in which case it has the same shape as the volume scattering function. But then as I go to further distances, the amount of multiple scattering becomes large, and these things flatten out there, and they don't look like the volume scattering function anymore because of the multiple scattering effects. On the other hand, they then approach something called the asymptotic radiance distribution, or the shape of it, which we haven't talked about in here, but that means you've got, lots and lots and lots of multiple scattering. And so that flattens out things. So just keep in mind, with the volume scattering function, there's nothing in there about distance, but with the beam attenuation function, or beam or point spread function, now that depends on the IOPs and on how far away you're making the measure. Okay, so here's the way this gets used. I'm looking at this shark here in the water. And let's say I'm looking at this point, X naught, Y naught. Now, some of the light that I'm looking at that point right there is coming from the background ocean. But some of the light I'm looking at this point actually came from, say, the shark's fin, but it got scattered in the right direction. And some of the light at this point here actually came from the shark's tooth, but that got scattered in the direction I'm looking at. And the further away I am, the more scattered it will be, and the more the rest of the image contributes to the point I'm looking at. So if I want to compute, what am I going to see when I look at this point right here, I have to integrate all the other points here weighted by the point spread function. So just think of this little circle here is contours around here. So I'm looking here, it's like I'm looking at this point right here, but I'm getting some of the light from this point over here. So if you write this down, it says, look, I'm going to look at this point X naught, Y naught. And that's the light that's actually coming from there, but it's also being attributed to by the point spread function from all the other points X and Y in this whole image. So I have to integrate over the whole image to get into the contributions of all of those other points to the point I'm looking at. And of course, I can convert from, X, Y image into a theta angle here, just because this little distance here is rho, that's just X naught minus X squared, etc. And this angle theta is tangent, or this is rho over how far away I am r. So I can go off and compute a point spread function as a function of r and theta, and then convert it back to values of X and Y, and use this equation here. Okay, so you can have a point spread function for the water, for your eye, for the camera, for the sea surface, whatever it is, it just totals up how the whole scene affects the point you're looking at. And then you have to evaluate, normally if I want to predict this image, I'm now going to use this for every point in the image, and I'm going to do this integration for each of those points over every point in the image. So it becomes computationally horrible. Well, anyway, the funny story here is Paula von Tempe at the, who was the NASA program manager of the ocean biology and biogeochemistry group for 18 years or so. She was in this class in 97, maybe, I don't remember, 95.
98.
When was it?
98.
98, okay. Anyway, she told me later that she's sitting in the class, I'm going through this crap, and she says, I don't need to know this stuff, I'm a biologist. Okay, so who cares about point spread functions? Then she goes to work at NASA. Second day she's at NASA, they have a meeting on the optics of the CWIFS instrument. And the whole discussion was about the point spread function of CWIFS, and the point spread function of the atmosphere, and the point spread function of the water surface, and blah, blah, blah. So she said she had to go out and, learn about point spread functions, and Kurt really knew she did need to know it, even if she was a biologist. So anyway, you've at least seen the words now, and you'll know when you need to know about point spread functions, you can go dig this notes out and kind of refresh your memory. Okay, so here's a photo of a sponge that I took from like maybe this far away, snorkeling when I was kayaking in Panama. So it's a reddish sponge here, and then you're seeing the background back here. Here's a prediction of what that would have looked like from 5 meters away in water that had 0.5 milligram per cubic meter of chlorophyll. So what do you notice? What's the difference in this image and this one? What stands out the most? Yeah. So the red sponge now looks almost black. What else do you see? Yeah, so in the background, here you're seeing a lot of detail of the coral and stuff that's in the background. Here the detail is pretty much lost. So you're seeing two things here. The high absorption by water has removed the red, and scattering by the particles in the water has blurred out the background. So both of those effects are built into the point spread function that I used to start with this image and do that integration business and compute this image here. And the math there is, well, it's probably like 30 pages or something, I don't know. And then a bunch of computer programming And you don't ever actually really compute this integral here. And actually for a digital image, that now becomes a summation over all the pixels in the image. Because if you have too many pixels, this goes up horribly in computations. But if you go over to Fourier transform space, then you can use a thing called the fast Fourier transform and evaluate this in a few seconds. But anyway, this is the kind of stuff I've been doing for the Navy. And of course, I have 3 beam spread functions or point spread functions, one for the green, one for the blue, and one for the red channels that you would have in a video camera. And then I can tell them, here's what you're going to see if you go out in the water with a video camera, and you've given me the spectral responses of the red, green, and blue channels, and I can use those to compute the corresponding red, green, and blue point spread functions, and so on and so on. And then you take an image like this that's coming out of a camera with an RGB, and you process each channel, and so on and so on. So anyway, just a comment here. Notice that this integral, it's giving me a function of x naught and y naught with at a distance r, starting with the image at distance 0, and then the point spread function at x minus x naught and y naught minus y naught integrated over all of x and y. So that has the form of my function, you know, and y is like x naught, and another function at x naught minus x integrated over all x, and I get a function of, in this case, I called it y, but over there was x naught and y naught. So integrals that have this form, one function times another one at the variable minus some offset, and then integrated over this offset, those are called convolution integrals. And they have all kinds of wonderful mathematical properties when you take their Fourier transform. And if this were a full month of radiation transfer lectures, we'd see how that works. But meanwhile, you can go read up on it in the Ocean Optics web book, or actually it's the book, it's not on the web yet. So the thing to note is that convolution gives another function. So these two functions give me a third function. If you just have an integral that says, take two functions, f of x and g of x, and integrate over x, you get a number, not a function. And it drives me crazy that people will write a paper and they'll say, well, we have the spectral irradiance that we measured in the ocean, and we convolved that with the spectral response of our sensor, and we got the value we measured. That's not a convolution. This is the irradiance in the ocean times the spectral response of the sensor. They integrated over all wavelengths, and they got the number of 1.2 watts per square meter per nanometer. And that's, you could call that just the integral of the products. You could call it the integral of f weighted by g, or g weighted by f, or whatever it is not a convolution. That's got to be like the second most misused term that I see in papers. And I always ding you when I read a paper or review a paper. Somebody says, well, we convolved whatever. And I say, really? And what function did you get from this? And I think you're saying you took it and weighted it and integrated. So that's just a little sore point. It's kind of like a manual goes ballistic when people put 7 decimal place accuracy on the numbers coming out of their AC9 instrument. And I can't handle people that either call irradiances and radiances AOPs. They're not, they're radiometric variables. And I can't handle people that call this a convolution. Okay, so this now gets us into the business of color, which is what your brain comes up with. So I'm telling you how beautiful icebergs are. And I said, just look at this spectrum of the light coming off of an iceberg. Isn't that beautiful? Well, about the most you can say is, I guess they are kind of blue, but I don't really get the beauty thing. But if I show you a picture of an iceberg and you see all the different shades of blue and everything, then you say, oh yeah, that's actually quite beautiful. So This is what you get out of radiometry, and the color here is what you get out of photometry. So how do we relate this spectrum to this physical phenomenon that we call color? Well, we go back, there's now 3 what are called tri-stimulus functions. One of them, Y here, is that photopic function that we were just looking at. And it peaks in the green. Then there's one that peaks in the blue, and there's another kind of funky one that peaks in the red. And these have all been cooked up by making lots of measurements of people looking at different colored lights and telling me, you know, this red light looks really bright now, and it doesn't look very bright here, and figuring out as a function of wavelength, your eye's sensitivity more or less to blue, green, and red. Now, the eyes are really a lot more complicated than that, but people have now agreed that we'll take these 3 tri-stimulus functions and we'll use those to define color in a quantitative way. So what you do to do that is you take your spectrum. So the F here, that might be this radiance spectrum right here, and I want to compute the color that goes with that spectrum. So I take the spectrum, I plug it in here, I multiply by this X bar function, the blue guy, or sorry, yeah. The red one is the X bar, the green one's the Y bar, and the blue one is the Z bar. So I compute these 3 numbers. There's our little conversion factor, 683 lumens per watt, and I come up with these capital X, Y, and Z. Now, these functions all integrate to 1 here. So when I compute these 3 things, and then I normalize them by the sum, then the little x, little y, and little z really all add up to 1 by this normalization. So they're not really independent. So we just by convention say, let's plot the x and y values here, and if I wanted z, I can get it. And I might add, these are for the normal white European male guys that they did all the experiments on. And of course, this was done back in the 1930s. So women and, you know, Chinese and whatever, they didn't count them. But they probably have about the same. Yeah, Ben.
Why do we see a peak at 450 in X bar?
Okay, very good question. Because they do what are called spectrum matching studies. So you look at one light that's shining whatever it is, you have another light next to it, and the person can dial this thing and make this light brighter or darker until they look the same. And then they come up with these curves. Well, what they found was in order to get a match, you had to have this little bump down here. So that's why it's not really how your eye sees red light, but it's just what they found that they had to do in order to get a way to describe what your eye sees. And it's actually quite a complicated business. So there's, needless to say, pages on the web book that kind of outline these spectrum matching functions and such. But after doing years and years of those studies, they just eventually agreed that these are the functions we're going to use. And they're now fixed in stone. Okay, and of course, if you're colorblind, game's over. Your eye doesn't have these functions.
Thank you.
Yeah. Manuel's colorblind. So he's got something else. Okay, so here, for example, if we have a 532 nanometer laser, and I want to come up with the color coordinates for that laser, what I do is I take the 532 nanometer thing, and I say, well, let's look at the X bar thing. Well, it's down here at about, I don't know, 0.03 or something. So the X value here, I plug in here, I do this, I do the conversion. I'm getting a lot more at green, and I'm getting almost nothing from the blue contribution. I compute those numbers here, and then I end up with a little x, little y, little z values. And so my XY color coordinates for this 532 nanometer laser will be 0.16 and 0.81. And if I have a 300 nanometer laser, it's down here. I don't get a color for it. 300 nanometers doesn't have a color. It's invisible to the human eye. So anyway, here's just an example of I would take this little delta function, plug it in here. It's really just picking off the values of these things at this point, this point, this point. So I add them all up, compute this. Then what we do is, since this little x, little y, little z add together to 1, their values just define a plane here. And so I've gone from the things I computed from the integrals, normalized them, and then we just plot the XY values, which I've shown here, and that's what's called a CIE chromaticity diagram. So I take this little plot here, pull it out, and plot it as a function of X and Y, and there that thing is. So you remember this 532 nanometer laser gave CIE coordinates of 0.16 and 0.81, and there it is right there. Now, so over 0.6 up to 0.81, 532. Now, the way these things are put together is if you go through this exercise for monochromatic light, starting out here at like 400 nanometers, and you work your way around and hit 532, and then out to like 720, that generates this row of points here, and that's called the spectrum locus. And then people have looked at this kind of thing and just kind of divided it up into regions, and they're going to call this is green and yellowish green, you know, yellow green, you know, fine around to red and around to blue. And then if you come back here and you put in that each of these the function you're putting in is independent of wavelength, that ends up giving you 1/3, 1/3, and 1/3 for these coordinates. So absolutely white light is at the very center of this diagram at 1/3 and 1/3, and that's called the white point. So the coordinates around here are very pure colors, like the 532 nanometer laser, and in here, this point is a mixture of all wavelengths equally. And if I have, let's say, a point right here, that's sort of like taking a 532 nanometer laser, but mixing in a bunch of other wavelengths as well. And then the other thing is, if you look at this, there's in nature, there's no such thing as purple light, for example. Purple is what you get if you mix red light and blue light. So you can't make a purple laser. You can make a blue one, you can make a red one, you can make a green. Well, this line connecting the pure blue color here and the purest red here, that's called the purple line. And so a point in here is a mixture of blue and red light. So that's just the terminology. Okay, so if you look at the chromaticity diagram, well, where's brown, for example? There's kind of yellowish and orangish and red, but there's no brown. Brown is just red light that isn't very bright. So to generate these figures, I just took IDL and I turned on all the pixels, the red pixels in my screen at a maximum value of 255. So the pixel brightnesses go from 0 to 255. I turned on the red pixels at their maximum brightness and just did a screen capture. Then I turned the red pixel down to 200 to 150 to 100 with no green, no blue. And you see the visual perception here is you go from red to kind of reddish brown to brown. But really, it's all exactly the same red light. It's just that your brain says, I'm going to call faint red light brown, and I'm going to call bright red light red. And if I keep cranking down the numbers, of course, then that eventually becomes black. And likewise, gray is just white light that isn't very bright. Okay, so the catch now is I can take the spectrum here and plug into these equations, and I come up with a unique chromaticity coordinate for that spectrum. But you can have lots of different spectra that give you the same chromaticity coordinates. So it's not unique going in the other direction. And those are called metameric spectra. And you can have, it's really crazy how this works. It's all your brain's fault. So for example, if I mix red light and green, I get yellow. If I mix red and blue, I get purple. If I mix green and blue, I get cyan. And if I mix all three of them together, I get white. So when you want to make a computer screen or TV, you don't need to have a pixel in there that's putting out yellow light. You just turn on the red pixels and the green ones, and it will look yellow to your eye if you're far enough away that you can't resolve the pixels. But we always used to do in the first day's lab, we would take a little magnifying glass and look at the pixels and look like right here, and all you see are red and green pixels lit up. We can't do that anymore because all the screens now are such high resolution that you have to have a microscope to see the pixels, so it kind of doesn't work. But the bottom line is your eye cannot tell the difference in true yellow light that peaks out at maybe 588 or green light and red light that are here and here. Your eye and your brain just don't see the difference. And so that's good, and it lets you make color TVs with just 3 different colored pixels. Okay, final topic here, there's a thing called the Forel-Ulla color index. This goes back to the 1800s when these two chaps, Forel and Ulla, they came up with mixtures of stable dyes, and then they put the dyes in little test tubes, put them in a little rack, and the colors went from a deep blue through green, through kind of yellowish and kind of to a brown. And so you can buy these little scales now, and you just hold it up, you look at the ocean, you look past the little test tubes, and you just find which little test tube does the closest match to the color of the water. And that's then the Forel-Ulla index. There's 21 different solutions here. And when you look at the bottom of the Hydrolite printout, it'll say, you know, if you do the run from 400 to 700 or more, then it can do these integrations. So it computes out the Secchi depth, then it computes out the CIE chromaticity coordinates for water leaving radiance, total upwelling radiance, KDs and whatever. And it also prints out the Forel-Ulla index, which I can compute given the other things. And so you go from, you know, very blue water up to green, yellow, brown with these different indices. And people use this, it's worthwhile. Yeah, Colin.
So you can buy one of these, they're very expensive. But they also, there's some instructions online that you can make your own, it gives you the actual compounds to mix up and how to mix up. So you can make your own custom full of these guys. It's actually a pretty exciting, fun thing to do.
And what's nice about both the Secchi depth and the Forel-Ulla index, especially with the Forel-Ulla, because our data going back to the early 1800s, because like whaling captains and stuff, they would have something like this, and you know, you're out for 3 years looking for whales, you might as well do something useful. So there's a lot of data going back to the 1800s where people have recorded Secchi depth and sometimes the color of the water. And so now you can look at those data sets and say, well, has the average Secchi depth and has the average color of the water in the South Pacific changed in the last 100 years. And there you start having another little data point that's climate change really changing what's going on in the ocean. So this fellow, Marcel Vernon, actually did a lot of work before he died on searching these old data sets and pulling out that information and putting big databases online now. So if you go to something like the Nomad database, I don't know if you search on Secchi depths there, how far back it goes, but that stuff is being pulled out literally out of old ship's logs in libraries in Nantucket or Marseille or wherever it is, and getting that information and putting it online for looking at long-term climate change. Okay, yeah, here's a chromaticity diagram with the Forel-Lula indices. So you see number 1 is very blue water and on around through the green to number 21 is this kind of yellowish, yucky, reddish water. And there's, rough little correspondences between, low chlorophyll, you're going to get Forel-Lula of 1, high chlorophyll, you're getting 10, so chlorophyll of 50. You're up here in the green water. You add in more CDOM, you add in more minerals, whatever, and you can get around to here. Okay, that's it. So here's a couple of photos of Antarctica. This was 2018. So I was over 70 then. I thought I was doing okay for 70. Anyway, as I said, we went down there, we kayaked along the Antarctic coast for a couple of weeks. And here's what the scenery's like. This is near a place called Cape Renard. It's just utterly beautiful. My wife, we both like to be in single kayaks, but if you want to do photography, it's nice to be in a double kayak and then you're not worried about turning over and ruining your $1,000 camera. But anyway, here we are. This is a place called the Lemaire Channel. So this is Antarctic continent. This is a little island here. Probably the most beautiful day of paddling I've ever done. We went along here, worked our way through here, went around behind this island and camped on another island. We had lunch over here somewhere. Just utterly spectacular. The wildlife is amazing. There hasn't been any whaling or hunting since the 1950s. So all of the seals and whales and such have no fear of humans. They just completely ignore you. You can just paddle up like, 10 feet away from the seal and they just look at it and go back to sleep. So there's a little fur seal, penguins everywhere. Here, there were twice we ran across cruise ships. And one day, as we were paddling along, this bunch of people from a cruise ship came along. So the ones in the background are from the cruise ship. And this is my group here. And here's a humpback whale just coming up, like 10 feet away. This big eyeball comes out of the water and looks at you. We played around with these 2 whales for like 30 minutes. And they actually came up and actually touched the boats. I think they were like checking us out just like you would reach out and see what a whale feels like. Just incredible. And then all of a sudden they had enough, they just swam down the channel and they were done with us. Penguins, incredibly stupid. This one got his neck stuck in between the guy lines of my tent. And all he could do is try to walk forward. They have no reverse gear at all. So all he had to do was back up for 6 inches, get out of the thing. And he just sat there, just walking and walking and walking until I went over, got him and picked him up, put him on the other side, and anyway he goes, Here's a typical campsite. My wife, penguins everywhere. And the brown snow, that's not dirt, that's out of the penguins. And so all night long, these things are sitting there going, and then they have these cute little tails and they raise their cute little tail and they go, and they spit out this like big tobacco blob of half digested like sardines and krill and stuff. So by the time we got home, like the lower foot of our tent was just like all of these like brown spots all over it. I must have used like 2 gallons of Clorox sterilizing everything. But that's what a typical campsite looked like down there. And, you know, it's just fabulous. And of course, the problem, if you look here, everywhere along the shoreline, it's just a cliff of ice. So there's very few places you can actually go ashore, and wherever you can go ashore is penguin colony, because they have the same problem. They need to get out of the water. So you camped every single night except one. We were in the middle of a penguin colony. Well, anyway, that's the story. So I hope I got everybody covered here for languages, and you know, you'll have to check my Hindi and whatever. Young, what's that one?
Although, yeah, they say it in the Spanish side.
Yeah, okay. So first time I've ever used a Basque word here. So anyway, yeah, I photographed this guy in Kathmandu one time. He's a sadhu. He's in Hindu philosophy. There's 4 stages of life. You guys are all in the brahmacharya phase, which is the student phase. And then you go into the householder phase when you're supposed to like get married, buy a house, get a mortgage, go in debt, do the baby thing and all of that. And then there's a transition phase when you start to retire and, you know, shove everything off on everybody else. And then the final phase, this guy is in, he has renounced all worldly possessions and family, moved out, and he's now working on achieving moksha, or release from the endless cycles of death and rebirth. So anyway, colorful place. That's it. You have now survived 12 lectures and 3 labs from me. And I know it wasn't pleasant, but you did it. So you now have at least as much reading to transfer theory as I could give you in the allotted time. But there's whole topics like this visibility business. You know, I could give a full week's lecture just on visibility. And it's all very interesting, and some of it's not too simple and some of it is. But that's it. So it's now 11:30. Yeah, I talked a long time here.